Seen this formula before in college algebra, and this problem coming up is similar to one we've done in college algebra. So you've got a sub 0 is the initial amount. When t equals 0, that's important for this next question coming up, and k not equal to 0 is a constant of growth or decay, and t is the amount of time. If k is greater than 0, then the amount a increases over time, and if k is less than 0, then a decreases over time. So the size p of a certain insect population at time t in days obeys this function right here. So we're already given the function. It says determine the number of insects at t equals 0 days. Now, the long way to do this is to put 0 in for this t right here. And 0.06 times 0 is 0. And then e to the 0th is just 1. And 800 times 1 is 800. Now, that's the long way. The easy way is just to recognize if you are asked about what's happening at t equals 0 days, it is just this answer right here, 800. So in the very beginning, they were 800 insects. What is the growth rate of the insect population? The growth rate is this number right here. Now that's a decimal form. What the answer is looking for is percent, so 0.06 is 6%. So this insect population is growing at a rate of 6% per day. Now it says, what is the population after 10 days? Now, 10 days, that is your t. If you look back at your function here, we're looking at the population as it relates, we're looking at the population as it is a function of time. So we're just looking at doing this formula. P of 10, because you want to know what's going on after 10 days, equals 800 e to the 0.06 times t, which is that 10 that's right there. So this is just a straight calculator problem. Enter in 800, second ln, which brings up your e, to the 0.06 times 10, and we have 1,458 insects after 10 days. This next one is going to require us to do a little bit of work. It says, when will the insect population reach 1,120? That means we're talking about this number right here being 1,120, and we want to solve for t. We want to find out when that happens. So that will be this formula. 1,120 equals 800 e to the 0.06 t, because we want to find out how long it takes for this insect population to grow to this. We know to solve any type of exponential equation like this, we need to get the exponential part isolated, so we divide both sides by 800. Over here on the right side, it stays e to the 0.06 t, and then 1120 divided by 800 is approximately 1.4. Now 1.4, just leave it on your calculator. To undo this exponential equation, we want to take the natural log of both sides. So if we do ln of both sides, of course right now you've got this whole number sitting on your calculator, so you can do the ln of that number by doing ln of second answer, and that comes out to be approximately 0.3365. Of course, leave all the number on your screen, but ln e goes away and we have 0.06 t. So what's sitting on your calculator is this big number, 0.3365, etc. Leave it there, and to solve this equation for t, we're going to divide both sides by 0.06, and t equals 5.6 days. Now, another formula that we did look at in college algebra is uninhibited radioactive decay. Very similar formula as the last one. It's just we're looking at this being radioactive decay. So a sub 0 is still the original amount, and k turns out to be a negative number because it is decaying. So we're going to do just about the same steps on these next problems coming up as we did a minute ago. So over here it says strontium-90 is a radioactive material that decays according to this function. So again, we are given the function. Part A just asks us what is the decay rate, and of course rate is always referring to the percent, and the percent refers back to this decay number right here. As a decimal, it would be negative 0.0244, but it has to be a percent, so it is still negative 2.44%. This next question asks how much of this material is left after 20 years. 20 years is your t, so we're using the same function, but now we're going to find a of 20 since t is 20. So a sub 0 is still the 400 grams that we started with. E to the negative 0.0244 times t, which is 20. So if you stuff all of that into your calculator, you will find that there are 246 grams left. So what this means is after 20 years, you'll still have 246 grams of this strontium-90. The next question asks something different. It says, when will you have 300 grams left? When means you are looking for t. So we're going to use this same function, but we're going to have different information to begin with. We want to find out when, which means we're solving for t. A of t is 300 because that's how much is left. A sub 0 is still 400. E to the negative 0.0244 t, and we need to solve this equation. To solve the exponential equation, of course, we first have to get it isolated, divide both sides by 400, and we get the decimal 0.75. It is still e to the negative 0.0244 t. To undo the exponential, we are going to take the natural log of both sides. Cancels out, negative 0.0244 t over here. And on this side, I'm not going to actually do the natural log of 0.75 yet. I'm just going to rewrite it as natural log of 0.75. Because to solve this for t, we need to divide both sides by negative 0.0244 on both sides. And of course, that leaves me the t on the right side. And then I just have to use my calculator one time to do this arithmetic. And when you do this ln of 0.75, be sure when the calculator gives you the front parenthesis that you remember to type in the back parenthesis. Otherwise, you're not going to get the right answer. And this will be 11.8 years rounded to the tenths place as requested. Years. Now, if you look back at this equation, this was our decay rate. What we don't know is what the half-life value is for strontium-90. Remember, your radioactive materials have different half-lives. We don't know what the half-life is for this material, but we can find it using this formula. So our formula says A of t equals A sub 0 e to the negative 0.0244 t. Now, one way we can go with this, and it's probably the way that you would understand best, is we're starting with the 400, and we're trying to find out the half-life. That means how much time elapses when there will be half of it left. So there's the 200 equals 400, etc. To solve this, I need to divide by 400, which just gives me a half over here, equal to e to the negative 0.0244 t. Now, what I did here with starting with the 400, cutting it in half, was to explain to you where this half comes from. But this little formula right here can be a nice little shortcut formula for determining half-life. All you have to do is set 1/2, because we want the half-life, equal to just the exponential part. You don't really have to think about it starting with 400. All I have to do is solve that little equation right there. So that's a shortcut to determine half-life of any material, as long as you have this formula over here. So ln of both sides, this is going away. I'm just leaving this as ln. I'm just going to put 0.5 rather than a half because it just saves me some room, equals negative 0.0244 t. Let's solve that by dividing by negative 0.0244 on both sides. Cancels out, and we just get t. And do this arithmetic, and be sure you keep the natural log of 0.5 in parentheses, divide that out, and it is 28.4 years. So the half-life of strontium-90 is 28.4 years. This law of cooling states that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. What this is talking about is this. If you've got a cake in the oven at 350 degrees, the second you take it out of the oven, it is 350 degrees. And you leave it out on the counter for a while, it continues to cool. And eventually it cools exponentially toward the temperature of the surrounding medium. What does that mean? How about your house is at 80 degrees? So that's your house. That is the surrounding temperature. So if we want to take this information over here to this formula, T is the constant temperature surrounding the medium. That is the 80 degrees in this example. U sub 0 is the initial temperature of the heated object. So this is U sub 0 because initially when you took that cake out of the 350 degree oven, the cake is 350 degrees. Now the other temperature we have to think about is this U of T. And what U of T deals with is, let's say we want to know that the cake gets down to 300 degrees because that's when we want to ice it. So that would be the 300 degrees. We want to find out how long it takes for our cake to get down from 350 to 300 so that we can ice the cake. So you've got 3 different temperatures to keep straight when you're using this formula. Of course, E stays E, K is a constant, T is still time. A pizza pan is removed at 9 p.m. from an oven whose temperature is fixed at 425 degrees. So the oven was 425. The second you take the pizza out of the oven, it's still 425. And what that is, that's our U sub 0. It comes into a room that is a constant 73 degrees. That is the ambient temperature. That is the temperature surrounding the medium. So that is our T. After 5 minutes, now that is little t for time, the pizza pan is at 300 degrees. That is your U of T. And all we have to do is take this information and plug that into our formula up here. So U of T, which, let's write this out so we got it in front of us. U of T equals capital T plus U of 0 minus T e to the kt. So stuffing in, U of T is 300. Capital T is 73 degrees. U of 0 is 425 degrees. Minus capital T, which is also 73. It is the same number. E to the K, which we don't know, times T, which was 5 minutes. So we've got some arithmetic we can deal with here. I can do 2 things at once with pretty easy arithmetic. Subtract 73 from both sides. Gives me 227 over here, so we're done with that. I can do what's inside the parentheses here. 425 minus 73 is 352. E to the 5k, that looks better than k5. We know we've got to get the exponential totally isolated. We're partway there. If we divide both sides now by 352, we will have the exponential part of our equation isolated. Now 227 divided by 352 is approximately 645. Keep the whole string of digits on your calculator, and this is e to the 5k. To undo the exponential, take the natural log of both sides, and I can do natural log of 0.645, all of those digits, by doing natural log of second answer, which is what brings up the 0.645, and this is approximately negative 0.44. Again, leave all of those digits on your calculator, equals 5k, because that cancels. Divide both sides by 5, and of course you are dividing this whole number, not just negative 0.44, and we get negative 0.0877. So that is our constant of cooling for this information. And knowing that we have to continue solving using this constant, I would stow this on your calculator as x. That way you've got not just the 4 digits, you've got the entire number stored on your calculator. This next question is going to ask us to solve an equation algebraically. Just as a reminder, here's the information we had on the other page. Here was our k value, but we've got it stowed in the calculator. So now it wants to find out at what time is the temperature of the pan down to 135 degrees. That is our U of T. So we want to find out when it gets down to 135. Capital T is still the ambient temperature, which was the 73 in the room. U sub 0 is still the 425 that came out of the pizza came out of the oven, minus the 73. e to the negative 0.0877. I'm just using those 4 digits, but I've got all of the digits stowed in the calculator, times t, because I want to solve for t. So again, we've got to get this exponential part here isolated. So subtract 73 from both sides gives me 62. We already know 425 minus 73 is 352. E to the negative 0.0877t. Divide both sides by 352 to get the exponential totally isolated. 62 divided by 352 is approximately 0.176. And this is still e to the negative 0.0877t. Take the natural log of both sides. Over here on the right side, canceling out, and I have negative 0.0877t. And I'm just going to leave this as ln of 0.176 there. I haven't taken it yet. And then remember the negative 0.0877 is actually stowed as x. So what I'm going to do with the calculator is divide by x, which is the 0.0877. But ln, so what you'll type in the calculator is ln of second answer, because what you had on your screen was 0.176, divided by x, and that should come out to be 20 minutes, rounding to 20 minutes. But it asked at what time. Remember, the pizza came out at 9 o'clock, so at 9:20 p.m., the pizza should be down to 135 degrees.